Good morning, dear students. Yes, good morning, everyone. Okay, so in the last class, what we have discussed, we have discussed about the pseudo first order reactions, right? Or they are also called as pseudo unimolecular reactions. So, what do you mean by pseudo unimolecular reactions? So, a reaction in which the molecularity is two or more, but the order is one. Okay, so or you can write it as a chemical reaction which appears to be a higher order but actually follows first order kinetics is called as what? Pseudo first order reaction. So two important examples which you have to keep in mind. Okay. So the two examples are, first is the acid hydrolysis of ethyl acetate, or you can take methyl acetate. Okay. So ester. So you're doing a acid hydrolysis of ester to give you alcohol and a acid, right? And the second one was this what? Inversion of cane sugar, that is sucrose, okay, in the presence of enzyme, that is okay, in the presence of enzyme like invertase, it will undergo hydrolysis inversion to give you what? Glucose and fructose. So these are the two examples, okay, of pseudo first order reaction. Then we had seen about temperature dependence, right? We had seen about the temperature dependence. Then we had discussed about the Arrhenius theory. So what was temperature dependence? That so at every 10-degree rise in temperature, the rate of the reaction also doubles, right? Then we had discussed about the collision theory. So collision, two important postulates we had discussed, that is, for every reaction to produce or like to form the products, it should undergo what? The reacting molecule should undergo collisions, right? So this was the first point. Then second term was what? So all the collisions which are undergoing, they are not effective. So these are not effective collisions. Okay, so only those collisions between the molecules will have certain minimum energy. Just a second. So all the collisions are not effective collision. Only certain collisions, okay, are effective. That is having the molecules. So they should have minimum amount of energy for the reaction, right? So that they will collide effectively and it will get converted into product. So this was about your postulates, okay, of collision theory, that is Arrhenius theory. So Arrhenius was the scientist who gave this collision theory. Then we had discussed about what is threshold frequency, right? What is threshold frequency? It is a minimum amount of energy that the reactant molecule should possess in order to bring about a chemical reaction. Okay, so this is about your threshold frequency. So whatever the minimum amount of energy which is required for a molecule to possess, okay, in order so that it will undergo a chemical reaction, it is called as threshold frequency. Okay, then we had discussed about the activation energy. What is activation energy? So the whatever the minimum energy is there, which is extra, okay, so the extra energy that the normal reacting molecule should require to attain that threshold frequency, it is called as activation energy. So these all definitions are very important. Then we had discussed about the effect of temperature on the reaction, right? So what we have seen that, so for every 10-degree rise in temperature, the rate of the reaction was doubles. Okay, for every 10-degree rise in temperature, the rate of the reaction doubles. So these were the graphs which we had discussed. Okay, this particular graph also we had discussed. Okay, how at every 10-degree rise in temperature, how the rate of the reaction was getting doubled. So these things we had discussed. Then we had discussed about Arrhenius equation. So what is Arrhenius equation? So Arrhenius, he gave a mathematical expression between the temperature and the rate constant. Okay. And what was the relationship? K is equals to A into E minus EA by RT. right? What is K? K is the rate constant, A is the Arrhenius constant, okay? Then EA is the activation energy, okay? R is the gas constant and T is the temperature, okay, in Kelvin. So these are the terms, very important. Okay, I have told you this particular equation. They'll ask you write Arrhenius equation with the proper terms, okay, with proper terms. So like that the question will be. So you have to write the equation and you have to tell what are the terms called as A. A is the Arrhenius constant. EA is the activation energy in joule per mole. Temperature, T is the temperature in Kelvin. R is the gas constant, okay, and its value is 8.314 joule per mole per Kelvin, okay. So this is about the Arrhenius equation, okay. So let us discuss now about how to determine this activation energy graphically. Okay, how we have given it theoretically. Okay, how we have given it the theoretically. So we said that Arrhenius was a scientist. What he did, he gave a mathematical relationship between a rate constant and temperature. Now we will see how this will work graphically on the graph. Okay, now what is the equation? So the equation is K is equals to A into E minus EA by RT. So what we will do, we will take log on both the side. Okay, take log on both side. Okay, now taking log on both the sides of Arrhenius equation, what you will get? You will get ln of K is equals to ln of A into E minus EA by RT. Okay, now next step, what we will do? So this is what into, right? Ln of A into B. So we can do it as ln of A minus B. Sorry, ln of A plus B. Right? So how I'll write? So ln of K is equals to ln of E raised to minus EA by RT. Okay, plus ln of A. Okay, so whenever you have ln of A into B, so it can be written as ln of A plus B. If whenever you have ln of A divided by B, it can be written as ln of A minus ln of B. So this is the simple mathematics, okay, using the logarithm. So ln of K is equals to ln of E raised to minus A by RT plus ln of A. So now if I take ln here, okay, common. So what it will be? So ln of K is equals to, okay. So we know that therefore ln of E is equals to 1. Okay, we know that ln of E, okay, it is 1. So what it will become now? So minus A by RT plus ln of A. So this is our equation. Okay, so this is our second equation. So first equation was the this equation. Okay, so this is our first equation. Second equation is what? So after taking logarithm, we know that therefore ln of E is equals to 1. So if you put ln of E is equals to 1, then it will be minus EA by RT. Okay, it will be minus EA by RT. Now what this equation 2 represents? Okay, if we take a graph, okay, if we take a graph, okay, here it is. Okay, so if we see this graph, okay, if we see this particular graph, okay, of ln of K versus, so I have taken ln of K on the y-axis. Okay, we have taken ln of K on the y-axis. Okay, and on the x-axis we have 1 by t. Okay, 1 by t. This is 1 by t. Then what we got? So we get a straight line. Okay, we get a straight line in a graph of ln of K versus 1 by t. Okay, this is a straight line. And what is the slope? Slope is minus EA by R. Okay, the slope is minus EA by R and the intercept is minus ln of A. Okay, the intercept is ln of A, not minus, it is ln of A. So the intercept is ln of A. So this is the graphical representation of Arrhenius equation. Okay, this is a graphical representation of Arrhenius equation. So when we compare the equation. So how it is looking? It is looking like y is equals to mx plus c. Okay, y is equals to mx plus c, where y is your ln of k. Okay, and m is your slope, that is minus ea by r. Okay, and x is your 1 by t, and c is your intercept, that is ln of a. Okay, so this is the Arrhenius equation when we write it graphically. So this can be determined graphically. Is it clear? Is it clear? How do we represent Arrhenius equation graphically?
Yes.
Okay. What about others? Any doubts? Yes? Fine. So, okay. So let us go for the. So this was when we are determining the this what determining the activation energy graphically. Okay, now we will see how to determine activation energy experimentally. Okay, how we can determine experimentally. So activation energy, okay, it can be determined experimentally. How? By measuring the rate constant of the reaction at two different temperature. Okay, so if you want to calculate activation energy, okay, if you want to calculate the activation energy experimentally, okay, what we have to do? We have to measure the rate constant. We have to measure the rate constant, and how the rate constant can be measured of a reaction by taking the temperature at two different this. Okay, so we can take the temperature, or at two different temperature we can monitor the activation energy. So now we have the equation. So therefore that is at temperature T1. Okay, so equation 2 becomes, so from the graphical representation, what was the equation we had? Ln of k is equals to minus Ea by RT plus ln of A. So this was the equation, we got it graphically. Okay, now what we'll do, we'll substitute T1 in this above equation. So in the equation 2, so this was equation 2, what we will do? We will put all the, wherever t is there, we'll put t1, okay, with respect to t1. So ln of k1, okay, because its rate constant will be different, is equals to minus ea. Ea is a constant, so we are not changing here. Then r is also constant. T will be t1 plus ln of a. Okay, so this is, I'll write it as 1. Now what we'll do at temperature T2, at temperature T2. So what happens at temperature T2? So ln of K2 is equals to minus Ea by R T2 plus ln of A. Okay, so this is the second. Okay, now what we can do? We can subtract equation 2 by 1. So if I take ln of K2 is equals to minus Ea by RT2 plus ln of A. Okay. So this I have to separate from there. So what I can do, I'll do like this only. Wait. So ln of, I'll take another color, just a second. Ln of K2 K2 minus ln of K1, okay, is equals to minus Ea by RT2 minus of minus of minus Ea by R T1. Okay, so ln of A and ln of A is common, so it is getting cancelled. Okay, it will get cancelled. Now do it. So what will happen? So we know that ln of K2 minus K1 is nothing but ln of K2 by K1. So it will become division. So is equals to, so what I'll do? I'll take EA RT1 this side. So I'll take minus common. So it will be EA RT1 minus EA RT2. Okay. Now ln of K2 by K1 is equals to, so what is common here? EA is common. Activation energy is common. So EA is equals to EA by R is common. Okay. So 1 by T1 minus 1 by T2. So we will convert to log 10. So this is ln. So let us convert it to log 10. So converting to log raised to 10. So when you are converting from ln to log, so what we have to put? We have to put the value of ln, that is your log, that is EA into 2.303 R. Okay. T2 minus T1, T1, T2. Okay, so this is the equation, third equation. So this is the experimentally we can determine the value of EA. So like this we can calculate so this is an important formula. By using this particular formula, we are going to solve problems. Okay, problems are asked for exams using this particular formula. Okay, so here you can see last one. Log of K2 by K1 is equals to EA by 3.2.303 T2 minus T1. Okay. So this is the particular equation. So here it is given C. Got it? So from Arrhenius equation, we have what? Ln of K is equals to Ln of A. So what we are doing? We are taking two temperatures. So for two different rate constant, we will get two different temperature. So by determining experimentally like this, we can get the EA, we can determine EA. So hence what will happen? Ln of K1 is equals to Ln of A minus EA by RT1. So for if you put T2, so this is for T2 with respect to D2, it will be Ln of K2 is equals to Ln of A minus EA by RT2. So if you divide equation this by this, okay, so you will get, so these are the steps. So by using this particular equation, okay, what we can do, we can get the we can determine EA. Okay, we can determine EA. Got it? Yes. Okay. So let us solve problems. Okay. How to calculate the activation energy? Very important. 3 marks question. Okay. So question is asked on this. How to calculate the activation energy. So please note these questions. Yes, so let us solve. First one, the rate constants of a reaction, rate constants of a reaction of of 500 Kelvin and 700 Kelvin are 0.02 per second and 0.07 per second respectively. Calculate the EA. Calculate the EA. That is your activation energy. Okay. How do you calculate it? So what is the formula? Yes. So we know that. Okay. So what we know that log of K2 by K1, okay, is equals to EA by 2.303 R. Okay. T2 minus T1, T1, T2. Okay. So put the values. We have the rate constants and we have the temperatures, different temperatures. So let us put the values. So your T1 is your what? T1 is your 500 Kelvin. T2 is 700 Kelvin. K1 is 0.02 and K2 is 0.07. Okay. And we know R value, R is 8.314 joule per mole per Kelvin. So K2 is per second, temperature is Kelvin, this is per second. So let us put the values. So log of what is K2? K2 is 0.07 by 0.02. Okay, is equals to EA divided by 2.303 into 8.314. Okay, then temperature T2 is how much? 700 minus 500. Okay, and 700 into 500. Okay, get the answer. What is the answer? Just check how much answer you have got. Do stepwise. So see log of 0. So 0.07 divided by 0.02. It becomes log of 3.5. Okay. Then upon EA divided by, so take 2.303 into 8.314. So this becomes 19.147. Okay. Then temperature you see 700 minus 500 is 200. So 200 divided by 700 into 500 is 350,000. So this two zero get cancelled. So this becomes 2 by 3,500. Okay, it becomes 3 by 2,500. Got it? Okay, so 2 by 3,500. Okay. Now, so what is log of 3.5? Next step. Next step. So stepwise you have to do. Don't get confused. So stepwise, let us go. So log of 3.5 is 0.544. Okay, is equals to E. Okay. EA by 19.147. Then 2 by 3,500. Fine. So what we can do, we can take EA on the other side. Okay. And we will transfer rest all the things on the this side. So it will be 0.544 into 19.147 into 3,500 divided by 2. Just see how much you're getting now. Just see EA value. Simple, simple maths. 0.544 into 19.147 into 3,500. Okay, divided by 2. So I'm getting 18,227. Okay, I've got 18,227 joule per mole. Okay, so I have to convert into kilojoule per. Okay, kg per mole. How much? Yes, 18,000. Yes, Sri Varuni has got it. Yes, a baby has also got it. Okay. What about others? Everybody has got the same. So this answer 18,200 something. It is in joules. Okay, it is in joules per mole. You have to convert it in kilojoules. So how it will be converted in kilojoules? So 18.22 kilojoules per mole. Yes, Yamuna has also got it. Very good. What about others? Other students? Yes. Did you get the same? So please note down these problems. Okay. In the notes, these problems won't be there. So problems things you have to write down. Okay. Got it? Okay. So let us go for next one. Yes. Should I clear this? Okay, fine. Let me clear this. Next question. The rate constant, the first order rate constant for the decomposition of ethyl iodide for ethyl iodide, that is C2H5I is a ethyl iodide, by the equation C2H5I gaseous giving you C2H4 plus Hi gaseous at 600 Kelvin is 1.6 into 10 raised to minus 5 per second. Its energy of activation is its energy of activation is 209 kilojoules per mole. Okay, so the rate constant calculate the rate constant of the reaction at 700 Kelvin. Fine. So this is a question. Okay. So what they have asked, the first order rate constant for the decomposition of ethyl iodide, okay, at 600 Kelvin is 1.6 into 10 raised to minus 5 per second. So energy of activation is given. You have to find the rate constant of the reaction at 700 Kelvin. Okay. So we have to find here what? We have to find here K1. So K2 is given. We have to find here K1. So we have the formula log of K2 by K1 is equals to EA by 2.303 R T2 minus T1 into T1 T2. Now, what all values we have will write. So T1 is there. T1 is our 600 Kelvin. Okay. K1 is 1.6 into 10 raised to minus 5 per second. Okay. Then T2 is there. T2 is 700 Kelvin. K2 we need to find out. Okay. We have to find out the K2. R value we have. R is 8.314 joule per mole per Kelvin. Okay. Got it? So now let us put the values. So here the formula is log of K2 is, we don't know. Let us write it as K2. K1 is 1.6 into 10 raised to minus 5 is equals to EA is, we have to, activation energy is also given now. Okay. EA is also given. What is EA value? EA is 2.9 kilojoules per mole. Okay. So let us put 2.9 divided by 2.303 into 8.314. Okay, into what is T2? T2 is 700 minus 600 and 700 into 600. Okay. So now do the value, do the calculation. So your log of K2 divided by 1.16, I can write it as log of K2 minus log of 1.6 into 10 raised to minus 5. Okay, I can write it like this also, is equals to, so do this 209. What you can do, 209 divided by 2.303 into 8.314. I got it as, or I'll do separately, wait. 2.303 into 8.314. So this is 19.147 divided by 209. So 209 divided by 19.147. It is coming to, I'll keep it at kilojoules. They have taken it as 10 raised to 3. Okay, they have taken it as 10 raised to 3. Okay, so they have given kilojoules, no? So what we have to do is we have to take 10 raised to 3 here. Okay, 10 raised to 3 means the 3 zeros will be added here. Okay, 3 zeros will be added. Fine. Now do this temperature. Temperature, you see how much it will become. 700 minus 600 is 100 divided by 700 into 600 is 4,000, 4 lakh 20,000. Okay. Now this zero, two zeros, these two zeros will get cancelled. These two zeros and this to see. So log of K2 minus log of 1.6 into 10 raised to minus 5. Okay, is equals to. So do this, how much you are getting? Just see. So 290 divided by 19.147. This is 109.15. Okay, divided by 1 by 42. 1 divided by 42 is 1 divided by 42 is 1 divided by 42. Yeah, it is 0.023. Okay, now see 109, 109.15 into 0.023. This comes to 2.510. Okay, 2.510. So log of K2 minus log of. So what I can do here, I'll shift this log of K2, I'll keep it on one side. Okay, I'll keep log of K2 here, and I'll shift. This is value is 2 point, how much? I got it as 2.51, 2.510 plus log of 1.6 into 10 raised to minus 5. Okay, so what will become? So see log of 1.6 of 1.6 is so what we have to do here? Just a second, I'll tell you. So okay, 10.94. What is 10.94? 10.91. Okay, 2.918. Yes. Okay, let me see. Okay. So here, understood up to here. Is it clear up to here? Please note it down till here. Okay, after this, I'll explain it. Yes, here you should get 2.9, 2.98. Okay, fine. 2.598. Okay. Up to here it is clear. Okay. So here's in point somewhere I might have missed. Okay. Is it clear up to here? Up to here it is clear. Should I clear this sides? I'll clear this sides. Okay. Fine. So now here what we have got, log of K2 is equals to 2.598 plus log of 1.6 into 10 raised to minus 5. So till here it is understood, right? Okay, fine. So let us go for the next here. So log of K2 is equals to 2.598 plus log of 1.6 into 10 raised to this. Now log of 1.6 into 10 raised to minus 5. Okay, how to solve this? So I have to take log of 1.6 plus log of 10 raised to minus 5. So log of 1.6 I am getting as 0.2041. Try see, plus log of 10 raised to 5 is minus 5 into log of 10. Okay. So this is how much? 0.2041 minus 5. So I'm going to get minus 4.7959. See, did you get the same? Try to solve. So log of 1.6 into 10 raised to minus 5. Okay, it is into. So into can be written as log of A plus B. Right. So like this. Yes, minus 4959. Good, very good. Okay, so this much. Now I'll put the values here. So it will be 2.598 minus 4.7959. So log of K2 is equals to, so what I'm getting here now, 2.598 minus 4.7959. It is minus 2.1979. Yes. So now log of, so it is minus. So if I convert it this side, so it becomes 1 by K2 will be 2.1979. Right. So if I take to denominator K2, so the minus sign will go. So 1 by K2, therefore 1 by K2. So log I'll transfer it in the other side. So it will be anti-log of 2.1979. Okay. So 1 by K2, the value of anti-log of 2.1979 is 1.577 into 10 raised to 2. Okay. See, are you getting the same? Then K2 will be equal to, so I'm transferring this. So it will be 1 by 1.577 into 10 raised to 2. So K2 value, you should get it as 0.634 into 10 raised to minus 2 per second. So this is the value of the K2. Are you getting 0.634? Yes, very good. Yes, Srivaruni has got it. What about others? Did you get it? Did you get this problem? Okay. Lubna has also got it. Yes. Okay, fine. So this is the rate constant. So like this, okay, we can calculate anything. Okay, we can calculate any one rate constant. Okay, we can calculate activation energy. Okay, so like this, the question is asked. Fine. So let us take another problem. Next problem. Let us take next problem. So now this you have to solve. Okay, this you have to solve. The rate constant of a reaction, rate constant of a reaction quadruples when temperature changes from 293 Kelvin to 313 Kelvin. Calculate the energy of activation of the reaction assuming that assuming that it does not change, it does not change with temperature. It does not change with temperature. Okay. So what is the question here? So I'll tell you. So what is happening here? The rate of the reaction quadruples. Quadruples means it becomes four times. Okay, it becomes four times. It becomes more. It becomes four times when temperature changes from 293 to 313. So what T1 is 293 Kelvin and T2 is 313 Kelvin. Okay. The rate constant K1 is what? It is, so the rate constant is K1. Okay. So, and K2 will be, K1 is, K2 is four times K1. So it is becoming four times when the temperature is increased from 293 to 313 Kelvin. What will happen to the temperature? The temperature is getting, the rate constant is getting four times. Now, okay, now what we know that log of K2 by K1 is equals to EA by 2.303 R. Okay, T2 minus T1 by T1 T2. Okay, fine. Now, so what is K2? Log of 4 times K2 by K1 is equals to EA 2.303 into R is 8.314. What is temperature value? Temperature is 313 minus 293. Okay, 313 into 293. Okay, so just see what value you are getting. So K1, sorry, what is K2? K2 is 4 times K1, not K1, K2. So it is K1. So K1, K1 get cancels. What is log of 4? What is log of 4? Find out. Log of 4. Log of 4 is 0.602 is equals to EA by 2.303 into 8.317. Okay, then find the temperature. 313 minus 293 is 20 divided by 313 into 293 is 91,709. Okay. So 20 divided by 91,709 is 0.000218. Okay. So this is the value. So what we can do here, we can take EA on one side, okay, and this will be 0.602 into 19.147 into, we can keep this like this only, okay, we can keep it like this only. What we can do, we will transfer this to, or we will take 20, no, so this will be 91,709 divided by 20. Okay, we can do like this. So what is the EA value, what you're getting? Just see, do like this. Okay, now you see how much of what, simply why to get complicated. So we'll do like this. So 0.602 into 19.147 into 91,709 divided by 20. So I'm getting it as 52,854.16 joule per mole. Okay, so if I want to do kilojoule, it will be 52.85 kilojoule per mole. Okay, or yes, Sri Varuni has got it. Then Baby has got it. Yamuna has got it. Yes. Fine. Is it clear? Okay. So two more problems are there. Yes, Lubna has also got it. Okay, fine. So two more problems. So next question. In a graph, of log k versus 1 by t, in a graph of log k versus 1 by t, the slope of a straight line obtained was minus 1.5 into 10 raised to 3 Kelvin. Calculate the activation energy. Calculate the activation energy. So what is given here? So in a graph of log k versus 1 by t, the slope of the straight line was 1.5 into 10 raised to 3. What is slope? Slope is nothing but minus EA by R. Right. So we know that log of k is equals to minus EA by 2.303 RT plus log of A. Okay, so this is our equation. So this is a straight line and the slope is what? We know that straight line is equals to y mx plus c. So what is your x is 1 by t and your slope is what? Slope is minus EA by 2.333 by R. So the slope is already given. Okay, the value of slope is already given. So let us put these values in the above equation. So what I'm going to get? So log of k, what is log of k? So just a second. Okay. Calculate the activation energy. So activation energy, so calculate the activation energy. So in a graph of log of k versus time, the slope of the straight line obtained was 1.5 into 10 raised to 3. Calculate the activation energy. So minus EA by 2.303 into what is this is 8.314 minus 1.5 into 10 raised to 3 is equals to log of k versus 1 by t. K versus 1 by t. So, okay, so this is get cancelled. So just see how much you're getting. So this will get transferred here. So 1.5 into 10 raised to 3 into 2.303 into 8.314 is equals to EA. Minus minus get cancelled here. So what you're getting EA? 28. Yes. 28.72 kilojoules. Okay. Very good. So 28 kilojoules. Okay. So take one problem for homework. Write down the decomposition of A into product has a value k is equals to 4.5 into 10 raised to 3 per second at 10 degrees Celsius and energy of the energy of activation is 60 kilojoules per mole. At what temperature would K be 1.5 into 10 raised to 4 per second. So this is a question. So a decomposition of A, okay, A into product has a value of K, okay. So here K1 is your 4.5 into 10 raised to 3 per second at 10-degree rising temperature. Okay, at 10-degree means what? Your this is 273. Okay, your normal temperature is 273. So 273 plus your 10-degree means it will be 283 Kelvin. So T1 will be 283 Kelvin. Then, and the energy of activation is given. Energy of activation is EA is equals to 60 kilojoules per mole. Okay, 62 kilojoules means 60 into 10 raised to 3. Okay, consider this. K2 will be, K2 is 1.5 into 10 raised to 2. Find your T2. So R value, you know, 8.314 kilojoules per mole. Okay, find out. So put all these values and see how much you are getting. Joule per mole per Kelvin. Yes, put the values and see. So all things I have told you, just solve now and see how much I have. You should tell me what is the value of T2. K1 is there, K2 is there, EA value you know, R value you know, T1 value you know. Find out T2. Yes. So log of 297. Okay, Sri Varuni has got it 297. Yes, correct. Others, others have got it. Yes, okay, fine. So whoever has not got it, I'll write the solution in the next class. Okay. Okay, log of 0.5229. Yes, so Bhagya has also got it. Yes, very good. Okay, fine. So I'll write the solution of this particular problem in the next class. So we have left with a very small part. Okay, that is effect of catalyst on the rate of reaction. Then we are going to see the collision theory of chemical reactions. Okay. So only these two important these are there. So let me do these things in the next class. Okay. So only two important This is there. So in tomorrow's class, your chemical kinetics topic will be finished. Okay. Is it clear? Fine. Okay. So the last problem, its solution, I'll be giving in the next class. So whoever has not got it, you please try. Okay. Still, if you don't get it, but tomorrow I'll solve that. Okay. Fine. So any other doubts? Any other doubts? So we have left with very two small topics, collision theory as well as the effect of catalyst. Okay. So that we will take in tomorrow's class. Fine. So no doubts? Okay. Fine. Fine. So I shall end the session here. Okay. Yes. We will meet in tomorrow's class. Thank you. Have a good day.